of wireless application areas, both technical and on the business side. He is now an executive director of network deployment at Verizon. And over there, he's in charge of both the network architecture and delivery of applications. So, and he's going to talk about application awareness, wireless networks. Thank you, Chris.
So how do I go to the next slide?
That's a question. It's right here.
Oh, got it. Okay. Well, I want to thank you for inviting me. My lawyers make me talk about this slide first before I talk about anything. So if anybody comes back and says, did I give a safe harbor speech? Yes. So Verizon's a publicly traded company, so anything I say here is not a commitment that we're going to do these things. So done. Okay. Here's the outline of my talk. It's going to be very similar to what we just saw. I'll talk a little bit about industry trends and a need for additional technologies, but then I'm going to focus a little bit on an intelligent content delivery for wireless. So there's, you know, as mentioned before, no silver bullet of a 5G technology that's going to increase the efficiency of the network 1,000 times. There's also, from a business perspective, even if we can increase the capacity 1,000 times so that people will use 1,000 times more, no one's going to pay 1,000 times more. So we have a business problem. We'll get into that a little bit and then go through a quick summary. So. Here's a background check for us. I mean, we all know this, that over the last decade or two, the shift from fixed telephony to mobile telephony has been pretty dramatic. You know, I was in the industry in wireless when I remember when our revenue went to 5% of the revenue of the phone company, and we were no longer classified as other revenue in the revenue statement. And that wasn't that long ago. And I remember how the wireless companies said, yeah, we finally made it to the point where we're relevant on the P&L statement of our legacy phone company, to the point now where, you know, we're almost the only thing that's important. So there's been a dramatic change there. And the same thing's happened already with broadband as well. Broadband, again, started out all fixed, and there's been a big push towards more and more going to wireless, so not too much of a surprise. These charts are actually on per 100 inhabitants worldwide, so they look like small numbers, but when you take them across the whole world, that's a huge penetration. So what's that show? There's this continuing movement from wired to wireless, and that it's going to continue. So let's talk a little bit about what broadband is, and the expectation of broadband keeps changing. You know, you can look in the yellow bar here. You know, this is from the fixed network over from '87 to now and beyond, what the expectation of the market is on what is broadband. So, you know, we're now, you know, in the 100 megabit per second services with Verizon Fios networks, really closely approaching a gigabit per second on the wired network to the, this is on the access to the premise. So there's this increasing demand, exponential demand for bandwidth. Now, on mobile broadband, there's also been an increase in expectations, but, you know, since the mobile bandwidth is limited, slower speeds are just inherent there. So there is an increasing expectation, but it's also always lagging behind fixed, and it always will. There's just nothing technically that's going to allow wireless to carry more traffic than a fiber to the home. So there's now look a little bit more closely on the device influence on the wireless side, getting back into specifically wireless. You can see I put in here the 2G, 3G, and 4G timelines, and looking also at what's been happening on the device side. And I want to pick out particularly the element there of camera phones being introduced in 2004. In 2004, networks were really 2G networks. You know, high speed at that time was 100, 150 kilobits per second. And I remember cameras coming out on phones, and it was a nice little thing to have so you could send little thumbnail pictures, but the network really wasn't fast enough to really exploit the capability of the camera. And then along came the 3G networks, where you're looking at hundreds of megabits per second, even a gigabit per second, and the cameras enabled, you know, things like the ability to post videos to YouTube and other things that were just never even contemplated in the 2G world when the camera phone came out, at least not from the operators. So we also see the same thing happening with 4G. It's really the advent of the tablets. What is going to happen with new capabilities of a tablet, a large screen, with 4G, with 4G speeds and 4G latency. So, you know, again, there's this combination of device, network, and application that really open up the value for the user of these wireless networks. So this first point here on this bullet, there's been a continuous move to wireless. Customers are at the point right now where they really are, there's a blur between wired and wireless. Customers want the same performance all the time, so there's a little difference between the expectation of how the applications will work, but we're left with this bit rate disparity. The wired network is always faster. How do we deal with this bit rate disparity going forward? Obviously, mobile households are commonplace, and I'll talk a little bit more on the next slide about this drive, especially towards video in the network and these statements that video will be 70+ percent of the entire network in a few years. So more in detail, this is some information from our networks and then projected into next couple of years of the breakdown of applications. Been a lot of talk about mobile VoIP and how much VoIP would be on the network, and mobile gaming being introduced a little more, especially with the low latency 4G networks, how mobile gaming is going to take off. But when you look at the bandwidth that all of those drive, dominant is mobile video. This video is, in this point, about 68% by 2014 is the expectation. So yeah, that's what we're focusing on, is how to deliver video over the network more efficiently. I also want to point out to 2 points on the points in the bottom 2 bullets. Kind of in the current state we are right now with, you know, most networks, 1 minute of video is around 2 megabytes of data. When you go to HD video, it's 10 times that, or about 20 megabytes of data. So the move towards the tablets, as I mentioned before, really enables the device to actually use HD video. Yet it's a 10x you know, increase in capacity that's used. So that has to be dealt with. And again, I'll state that the expectation from the market is, I don't care if I'm wired, I don't care if I'm wireless, I just want my content any way I can get it, and I don't want to pay more for it. So I just put this slide in here to show the lack of ability to plan. So this is the video impact of one particular application and a change of a business model on the internet backbone. And this on the right is AS701. That's the UUNet network, Verizon Business's core portion of the internet. And you can see in that fuchsia color, over a year period, a unknown application became 37% of the total internet traffic on Verizon Wireless or Verizon Business AS701 internet backbone. And that was introductions of the business model with Netflix. So over a 12-month period, you know, it took up 40% of the bandwidth of the backbone of the internet. So our ability to predict what the next change of business model over the internet, you know, we just can't. We have to have a flexible network because we can't predict what it's going to be, and you know, you can't react in the core of the internet to you know, quadruple the size of the internet over a 12-month period, and a lot of this is because of this expansion here. In this case, was because of an unoptimized CDN route of Netflix business model. So okay, back to my perspective I was trying to get at, is looking at the business challenge from an operator standpoint. You know, we know it is terrific that customers want to use our network. We see this huge potential for growth, 1,000 times, as was mentioned in the previous speech. You know, we were looking at trying to do a modest 66 times over the next 4 years. But with this huge growth of traffic, you look at the red line here on the right, a nice modest increase in revenue at the same time. So the question is, if cost does not go down significantly as traffic grows, we can't maintain a business model that makes sense. So if our costs are linear with that traffic growth, this business model breaks down, and we want to do everything we can to prevent that from happening. So the key is we got to significantly reduce the cost per bit per hertz. So it's not about adding capacity. It's not just about methods of adding capacity. The methods of adding capacity have to be at substantially lower, higher efficiencies or lower cost per bit. So I think this will complement what was mentioned in the previous talk about, efficiency. So over the last, 20 years, the wireless networks have improved their efficiency measured in bits per hertz, bits per second per hertz, from when we were in amps to CDMA 2000, with a spread spectrum CDMA, to EVDO when we went to put a time scheduler in there to take advantage of scheduling to make sure all users were only transmitting in optimal conditions. Improvements in Rev A and now LTE. We've really come to the point where we feel from a macro cellular network, we are right at Shannon's limit. So mentioned earlier, you can do interference cancellation and other interference techniques to move kind of to the far right on this SNR chart so that you can get 256 QAM as shown here. But to effectively get a 20 dB SNR per bit is in a macro wireless network, it's just probability is 0. So we really are operating on that 5 to 10 dB range and taking advantage of when it's lower. But new architectures so that we can move to the right on that graph are terrific. But there's not going to be a new 5G technology, a new something above OFDM that's also going to magically take us to 20 bits per hertz in low SNR. It's just not capable. So we have to find other methods of dealing with this. So that was kind of the background, and I want to get now into what we're working on the content delivery side of this. So yes, we need the HetNet solutions. We need all the capacity methods we can. I'm going to look here on the application side and say how can we deliver applications seamlessly and more effective. So in this example, the eNode B is depicted here on the right, and by that cube there is the scheduler and what's going on. All the flows are coming in individually, and the eNode B is deciding through what each flow has a queue statistic going on there. There's demand capacity, there's neighbor cell coordination, radio congestion considerations, and millisecond by millisecond, a decision is made on each flow of what resource allocation blocks to give to each application in each user. So the eNode B is doing that, and it is designed to the optimization problem there is to maximize throughput, aggregate throughput to all of those users, essentially. So what we're looking at is how, on the left, to start looking at the application side as well and put some intelligence in the application and how we're delivering content or delivering those flows to the eNode B in such a way that the eNode B can continue to just optimize towards capacity, and we can do a quality of experience optimization on the left-hand side of this. So I'll give you an example here. In an uncongested cell site, if a user has an iPhone and they're asking for a 1080p video and there's no congestion on the network, even though the display is really not good enough to display that entire resolution, you could just let the traffic go through. In the same situation where the site is under, say 90% load, and you've got a iPad tablet asking for a 1080p video, and at the same time an iPhone asking for a 1080p video, having an intelligent decision in the network to say, we'll let the iPad go and we'll take the iPhone resolution down to a point where it's matching its display capability. We can then let the eNode B do its processing, push both those flows through separately, and we've given the quality of experience to the user in a fair manner and maximized QoE, not throughput. We've given one device more throughput than the other, but by looking at the application, manage the quality of experience to be the optimization problem here. So there's many other applications you can do with that. One of them is a background application if you're upgrading your Angry Birds program and it's done in the background, the user doesn't even know. By rate limiting that flow and allowing the other flows to go through the network, you've essentially created a higher quality of experience and not put, not overwhelm the network. So that's really the angle we're doing here. So here's how we're doing it. This is the simplified diagram. In blue is the standard 3GPP and 3GPP2 equipment, the base station, RNC, PDSN, the SGW, and the gateways. On the far right there is the internet where the content is. And all of the techniques in red are what we're putting together in this contextual aware, service aware decision-making function that also pulls the statistics off the RAN and knows which sites are congested and which are not, and then makes flow-by-flow decisions on optimizing QoE. How do we do that and maintain a high-quality experience for all the users independently? And then you steer in services as needed to maintain that. So what that gives here is first the improved quality of experience. Let me go back here and show. One other thing that's I didn't talk about before, but in green is the CDN cache. At some point, content does need to be cached close to the edge of the network, and this is the perfect place in our interpretation of where to cache content so that it is close to the edge, not all the way out to the edge, but close enough to the edge so this contextual aware steering can take advantage of it when needed. So that's one of the things that leads to this improved QoE. That's where we're seeing that's the lowest possible application latency, not necessarily the RAN latency, but the application latency can be the lowest possible to minimize things like video stalling and then I talked before about device-aware delivery, so you can deliver the correct version of the content to the device. There's RAN modeling, again on a sector-by-sector basis in near real time, so that these decisions can be not made arbitrarily. Making arbitrary decisions, we don't, as an operator, want to make decisions about how our customers use the network. We're often, our industry sometimes takes a bad rap for wanting to control how applications work. We really do want to make applications efficient, but we want to do it in a way that is, under just good network management techniques, and having RAN statistics in there, know exactly when a RAN is congested or not, gives us an ability to say, no, we're really doing this to maintain the quality of all the users in the sector. So it's better to lower people's throughput in a time where, alternatively, if we hadn't done that, the videos would have stalled. So that's the type of direction we're after, and why we feel the RAN modeling is very important to this. And that leads to the content optimization when need be, and analytics to help us run and manage the network. So this architecture gives us all four of these. And again, the objective is to let us run the network in this advent of this huge wave of usage that's coming at us that frankly we want to support. And we do know that we do have to support it as much with methods like this, methods as mentioned before with HetNet and small cells, but we have to significantly reduce the cost per bit, or our customers, we won't be able to offer 2 gig, 10 gig, 20 gig plans. An unlimited plan that people are using 100 gigs of data a month that may end up costing a network operator $500, $600 a month to provide, just aren't going to be effective in the marketplace. So we do need to have methods where we manage applications when need be, and allow technology to come in and give us capacity in other ways. So again, video is the driver of this. Customers don't care if it's fixed or mobile. They just want access to their content. The video delivery architecture, I talked a little bit about being network aware. That's the device aware. We also can have this be HetNet and SON aware, so we can see if the delivery is over Wi-Fi, or deliveries over the macro network, or the deliveries over a HetNet microcell. There's different parameters that can be used there to say how do we best manage this traffic to maximize quality experience. Again, the application, whether it's a real-time application or non-real-time application, the decision function can be made there, and then again the device awareness. What can the device actually display? If we do have to take some things away from the subscribers, we want to take it away in a fair way, so that that they can see the bits that they're able to actually display on their screens. And this, if we do this all well, will enable a cost structure that allows us to grow into this tsunami of traffic. So that's what I've got. Open up to questions. Sir? Yeah, yeah, that's a really great question. So, yeah, the question of is the device tethering? If does the device have, for instance, an HDMI output? You don't know. At some point, we do. We do know on our devices which don't have HDMI ports, so we could look at that and say, yes, we know that that can't be actually going out to an HDMI port. So there's still some device intelligence where you can make some decisions. As far as the net neutrality concern, there's two aspects of net neutrality that are they're at play here. One is net neutrality allows us to manage the network, use network management techniques when appropriate. So it does open that up. So again, the RAN modeling. So we know a site's congested. The alternative is to do nothing and let the application stall or do something. So having that device awareness or the network awareness puts us in a position where we can go to the FCC and say, yes, look, we're doing this only in this cell that's congested. The second part of net neutrality is that we have to be neutral towards that. We can't take, for instance, a stance that would say, well, we'll slow down those videos for YouTube coming in, but Verizon has its own video service and not lower those. So we have to treat them all the same. So to stay within net neutrality, to treat everybody the same, but still allow us to change rates of application to deal with network congestion. So that's the net neutrality angle on this. Any questions? Yeah. Okay, I see the application delivery not needing any more standards work, if that was the question. Certainly there's more standards work required on how to do some integration of HetNet and then take tools like this into that. But no, this doesn't need any standardization or here.
Your traffic models look like they're applicable to the downlink. Will the uplink much the same in terms of allocation of video, for example?
Yeah, that's one of these. So the question is, all my discussions here were really from downlink focused. What's the impact of traffic conditions on the uplink? And that's one reason I put in the slide about Netflix and the changing business model. So currently my answer is no. Managing the downlink effectively manages the whole network. I mean we're downlink limited, and all of the applications that currently run are asymmetrical applications. And so if we can manage the downlink capacity to usage to match our capacity, the uplink is usually balanced. However, if applications change and more symmetrical applications start showing up, video telephony where it is symmetrical, then other techniques are needed. But this was mostly focused, you're right, on downlink applications, because that's predominantly what we see in our network today. Question here?
Just to be the annoying academic, I think the channel limit that you put is a point-to-point setting, and I think some of the unresolved issues on the signal processing information theoretic questions is how, with the number of links growing, how the network as a whole will grow in terms of throughput. And I don't think the channel limit will answer that question. It's how close you are with the link capacity. It doesn't still say how we can manage multiple links.
Okay, I agree. Here.
In my opinion, there are a lot of underutilized Wi-Fi capacity that are privately owned. Can you think of creating a business model or some kind of market that allow those privately owned Wi-Fi networks to be used in a fair and mutually beneficial manner as part of the heterogeneous network?
Yeah, so the question is, can you take advantage of Wi-Fi networks that are not carrier-owned, that are owned by others in HetNet? And yes, absolutely. We need to use all possible spectrum to deal with hotspots of capacity, and we currently do that in our network in large stadium venues, where we would, work with, cooperatively to build the networks, but it's not even owned by us, by Wi-Fi networks, and take advantage of those. So we clearly need to take advantage of all spectrum possible.
Is there like a market, give and take, like some kind of sharing of dollars
Um,
to give an incentive for Wi-Fi?
it's always case by case, so yeah, I can't really comment. Don't know. Back here?
Can you share with us how much data volume in, say, megabytes or gigabytes, your median broadband customer is using around now, and what you project that to be in, say, 5 years?
Okay. So right now it is X, and it will grow on that curve that I showed. So.
Some time ago, I don't remember exactly when, I saw various proposals of taking cellular phones and having those packets tunneled through Wi-Fi so that the traffic is sort of proxy through to Wi-Fi, so that from the perspective of the backbone network is seeing that traffic is being moving, so that you could use the wireless modem as well as the Wi-Fi in a transparent way, because it's tunneling the same traffic, it's just going through two different virtual networks. Has that taken off, or is that coming?
That is coming. That's a good model for several applications. So again, this is having, think of it as a tunnel that's connected to a Wi-Fi and also connected to towards the user, and then an LTE and maybe a fixed network connection in. So you think of it like an ATM machine that can have an LTE backhaul when the landline is lost. So you could switch between the two. There are many wireless backup mechanisms that are currently taking advantage of that, that make a lot of sense. One of the we don't see that as the main method for instance, doing femtocells. We look at a femtocell where you want the application to choose Wi-Fi or wide area, and not have it be an either or. It can be on an application by application specific multi-APN approach. So when we look at a combination of Wi-Fi and LTE in a femtocell environment, we want the device to, for instance, default voice applications to the LTE network, and video and web browsing to the Wi-Fi network, so that if the person actually gets up and leaves their house, that there's call continuity. So that's how we look at those.
Is the usual business model for a femtocell, is that something that's being owned by a carrier, or would it be?
Yeah, the business model for femtocell is the femtocell is owned by the user, and not by the carrier.
You have no influence over how that's, or how does that work in terms of how resources are used?
Yeah, one of the reasons why the femtocell needs to be, in our mind, owned by the user is if it's owned by an enterprise like ourselves, we have to keep inventory of it, and we have to know where it is and be able to, it just becomes impractical. So moving it to a user ownership model makes practical business sense for
So
RET.
like a boundary condition, are they using your resources at all, or are they just connecting?
I'll follow up with you. I'm getting the hook here.
Thanks.
Yeah.
Okay. Thank you. Thanks. Thank you very much.